So we are going to be walking through some of the pros and cons of using Sway, what it's like to develop smart contracts for the FuelVM, and just some general use cases through this talk. This talk does presume some level of elementary familiarity with Solidity, programming, preferably Rust, but not necessarily because this is the syntax is very Rust-like. This will also contain a lot of code examples and A/B comparisons, essentially amounting to tutorial or introduction to Sway for somebody who only knows Solidity. And yeah, I'll go ahead and get started. Cool. So we'll go ahead and start by kind of top down. What is the market that we're addressing? What is our motivation? Sway was motivated by both Solidity and Rust. So in Solidity, obviously it's like the prominent smart contract development language, and it brought the whole notion of smart contracts into everyone's mind, and it's extremely powerful. We believe in the Rust philosophy of language design, and we want to combine the ergonomic first-class smart contract and blockchain support of Solidity with the design philosophy of a language like Rust. What we generally mean by that is that we want to provide security and static analysis in exchange for auditing and being very careful. So the programming model is pretty similar to Ethereum, although we allow for multiple native assets. And this removes the error class of rolling your own token from your contracts entirely. There have been a couple of prominent vulnerabilities along that space. And that's kind of like what you would gain from coming from Solidity. But to talk about the Rust side of things, Chromium has done a study of all of the bugs that they have encountered over the past, I don't know, N years. We'll have to check the study. And most of them related to memory unsafety problems. And among memory unsafety problems, there's a couple different classes, but most of these are addressed by a programming language called Rust. Now, this is not a blockchain language. This is just a general purpose programming language. But what they were able to do is through language design and through static analysis, they were able to essentially eliminate an entire class of bugs, that represented 70% of the Chromium project's bugs. So just by virtue of language choice, your entire space of bugs is only 30% of what it used to be, which is huge. And we essentially want to do that for the smart contract development space. Obviously, memory safety bugs are not exactly a huge issue in the smart contract development space because it's a different problem domain. So we do not specifically tackle things like the borrow checker or use after free or things like that, mainly because they're not relevant. Instead, we provide blockchain-first static analysis, so things that typical contract vulnerabilities that you would want to catch. An example of that would be a violation of the checks effects interaction pattern. We can provide static analysis to warn you and prevent you from doing that without ever having to hire a single auditor. And if you want to see, they also have a pie chart about the various memory unsafety bugs they had in Chromium. Right. So we're essentially, my thesis here is that we're combining a lot of aspects of Rust and a lot of aspects of Solidity. So from Rust, we get a statically typed, verbose, and friendly compiler. We get the syntax of Rust. We get trait-based inheritance. So I don't know how many of you have dealt a lot with Solidity inheritance structures. It can be opaque, and the evaluation of constructor order can be ambiguous at times. Not technically ambiguous, but it's difficult as the programmer to analyze. We also, from Rust, package our compiler with a lot of tooling. So one of the things that Rust does great is cargo. So before I keep going, has anybody here used cargo before? Maybe a show of hands. Cargo, okay. About like 15%. So cargo is a package manager, a builder, a documentation generator, a augmentable plugin system, a testing framework, a benchmarking framework, all of that in Rust in this one single binary. And what that gives you is that gives you one enshrined way to do things. So you get a unification of documentation. You just skip that whole decision process of your tooling for a lot of these things. It gives you one unified way to build your project. And it gives you a lot of ergonomic benefits. So we package Sway with something extremely similar to Cargo. We'll get back into that later, but essentially, it's a batteries included pack. You just download the single binary and you get going. In addition to that, we have a unified team. So our tooling team, our language team, our formatter team, our VM team, we're all in the same chat here, right? So we literally the same Slack channels. So we're able to share a lot of code. We're able to unify our tooling. The main dichotomy that I'm drawing here is if you're writing a Solidity smart contract, you also need to onboard into JavaScript typically and use Hardhat, and you need to decide which testing framework are you going to use. You need to decide, you have to make a lot of decisions, and you have to accept a lot more liability. Having one enshrined toolchain eliminates a lot of that. So what did we take from Solidity? Well, our language is designed primarily around smart contract development. We integrate contract storage as a built-in language construct. So with a lot of other Rust-based smart contract languages, you'll see essentially storage access or other contract primitives as library functionality or as syntax, syntactic sugar or something like that. We have contract storage as a first-class language construct, but we try to do it a little bit safer than Solidity. We want shareable contract interfaces. So if you're writing something to call a contract, or if you want multiple deployments to implement the same interface, we want that to be able to be shared. And we want the tool to feel like it was made for the task. So you want to use the right tool for the right job. There are a lot of other projects that essentially bolt into Rust or use LLVM or like an alternate LLVM backend for the task of writing smart contracts. And what ends up happening is your front end was engineered for an entirely different purpose. And so you end up throwing away a good chunk of functionality and bolting onto a very specific subset. And it's just not an ergonomic feeling. And when you don't feel ergonomic writing code that is, deploy once, live forever, you're going to end up with vulnerabilities. So we are Fuel. And what we want to do here is we want to provide fast and efficient contract deployments and execution. And we want to provide safe code. We want everything to be easily auditable. We want you to feel safe when you're deploying any sort of contract written in Sway. We will maintain Semver and backwards port security fixes, which is something that has been a point of contention in the smart contract development space. And we generally just kind of keep an eye on Twitter, and we learn from angry tweets as well. I would like to mention that. And we unify the tooling and developer experience, as I mentioned before. So I'm just going to slightly tongue-in-cheek show a couple of angry tweets we've learned from. So yeah, so this one, well, I'll just play these really quick. So yeah, we also don't have that. And yeah, okay. So some people would say that Rust is definitely something that's hard to learn, but we're not writing Rust, so we aim to have a lot of really good documentation and a lot of really good developer onboarding. Okay, so I'm going to start getting into like the nitty-gritty language features. Specifically state variables. So when you're accessing contract storage or contract state, then in Solidity, it looks a little something like this. And this variable is essentially in your scope now. You have this stored data variable, and this in itself has, of course, led to some vulnerabilities, this ambiguity between which variables are storage and which ones are not. So what this looks like in Sway is we have this storage declaration, which looks really similar. It's a little bit different syntax, but we have the storage keyword, and we have, it looks like a struct declaration, essentially. And now to access that storage, you have to, in your function, annotate that you are accessing state with that annotation there that says storage read write. And you also have to prefix your access with the storage keyword. Now this seems like maybe something trivial. You're like, oh, it looks like a struct or an object access in any other language. But in reality, this would have prevented large vulnerabilities. Oh, I've done something to my presentation. In reality, this would have prevented quite a few vulnerabilities that are out there right now where there's ambiguity between whether or not you're accessing storage or whether you're accessing just a local variable. All right, and then we'll take another look at a couple code examples here. So, functions in Solidity, I'm sure nobody needs a refresher. They look more or less like this. You have attributes that you can attach onto your function signatures. You have things like pure, you have payable, etc. Just to give you a little bit of the syntax, in Sway, it's going to look a little bit different. So you define your ABI completely separately, your contract ABI, And this grants you a couple of things. So one is that you can share this ABI, you can export this ABI, and when you call this function, you can just import the ABI and use it directly, as if it was, just a library. And then we're going to implement that ABI for our contract, and you implement the functions. It looks a little bit like a trait, if you're familiar with Rust. And one final little thing is that we have implicit returns down there. So you see that there's no return keyword in the helper function. And then to go back a little bit to a different example, instead of having things like pure, payable, et cetera, we have these annotations on top of functions, function signatures. So that's just a syntactic difference. Yeah, and we've replaced the Solidity inheritance constructor system, as I mentioned before, with a trait-based inheritance system. If you're familiar with Haskell, it's kind of like a type class. If you're familiar with Java, it's going to be a little bit more like an interface. All right. Another thing that we want to look at is error handling and how you actually would handle an error case in a contract. So one thing that we really like and want to keep using from Solidity is being able to just revert in your control flow. This is not actually the case with all platforms out there right now, so we want to be able to retain that. So reverting in your control flow is great because you want to do one thing right or revert. That's like a really good design principle. So in order to keep this principle, we have retained that as well. And it looks like on this computer, my fonts are a little bit different. So we get a scroll bar, unfortunately. By the way, just since we see the scroll bar, if you ever want to look at this code right now or something, the URL is up there at the top. You can just browse to it and look along. You can even read my speaker notes. So that got louder. We have the panic macro, which I am. Okay, we'll move on from this one. We have here it is. Okay. So scroll bar is a little bit less bad here, but we have the transfer function here, which returns a result. So this is what's called a sum type, and we have enumerations in Sway. And what you do here is you can return an error, and if you're familiar with this, what this does is it instantiates one type of the sum type, and then that can return from your contract. All right, so another thing we have is along with our static types, we have a pretty advanced and robust type system. We have generics, we have type inference, we have structs and enums, which are also known as sum and product types. Or if you're particularly mathy and maybe even silly, they're called pi and sigma types. So what those generally look like is this. So struct, if you're familiar with Rust, this is almost the exact same syntax. The enums are a little bit different. But if you're familiar with Rust, a struct declaration, you're now declaring two U64s, unsigned 64-bit integers, that will be stored in memory contiguously. There's no overhead here, there's no runtime. The size of the not enough fun struct is 128 bits. It is two U64s concatenated together, and that's called a product type. And then for the sum type in the enum, you have one or the other. So instead of having memory being laid out contiguously, in an enumeration, you are either one or the other. This does have a little bit of overhead. There is a tag stored. So you have essentially 64 bits more than the size of the largest type. And as you see here, we have generics as well. So generic functionality so that you can share this sum type over all your other types. So our type system is essentially the same as Rust, but with a few differences. Primitive types are mostly from Solidity. There's a lot of primitive types in Rust that you don't really need when you're developing a smart contract. So our primitive types include unsigned integers, booleans, static length strings, 32-byte values, single byte values, and the unit type, also known as the MC tuple. And we also have tuples as well to compose these types. As mentioned before, we have generics and traits with inheritance. So if you're familiar with Rust syntax, this will be pretty familiar. If you're not, a quick explanation is that the trait is called foo. So this is, like I said, a type class. If you're familiar with Haskell or Java, it's like an interface. You're essentially opting into some interface for your type. So this trait here is essentially saying we're going to define a trait foo that is generic over two types. And the first type requires that it also implements the interfaces bar and baz. And the second type, E, requires the interface I've actually never had to pronounce this out loud. Kooks. There, we'll go with that. Yeah, so that's our type system. And then a couple of literal instantiations we have here. So generally, instantiating a variable, you can provide a type annotation optionally, or you can allow inference. We have B256 literals, et cetera, et cetera. So we can dive a little bit into the use cases of a union type, a discriminated union, which is a sum type, also known as an enum. So this is an example of composing those two things. So you have the structs with your contiguous memory layouts, and then you have the enumerations sale. So the struct service is the larger of the two because it has a 15-character long string, and thusly the size of sale, if you remember what I said earlier, is the tag plus the larger variant. So it's going to be the size of service plus 64 bits. Cool. Additionally, we have match expressions. So similar to Rust, you have control flow where you can put an if or a match on the right-hand side of an assignment. And what that does is it's a very expressive way of writing your code. And not only do we have matches as expressions, but we have exhaustivity checking. So there's actually, if you were to try to compile this, you would get an error because you are not covering the domain of numbers from 3 to infinity. And exhaustivity checking is another thing that essentially prevents vulnerabilities. Vulnerabilities oftentimes come from control flow that the programmer did not anticipate. And if the compiler is able to look at the control flow and say, hey, there's a case here that you've missed, you will not have an unanticipated case or undefined behavior in your control flow. So another quick example we'll dive into here is EC recover. So if you use EC recover in Solidity and it fails, you get a magic constant back. Doesn't quite fit with this font. And that magic constant is just a bunch of zeros. And this is generally considered as kind of a programming anti-pattern because what you have is a sentinel value that represents something. However, the sentinel value is within the domain of what could have hypothetically been returned from the function in a valid use case. And what this means is that the programmer has to remember to check for this every single time. If not, that's a potential source of vulnerability. And in Ethereum, this is not an issue, but in general, this is also a opportunity for somebody to like hijack whatever the sentinel value is, and that could lead to a compromised account or something like that. So one of the reasons we're really big on sum types and enumerations is that they completely prevent this. Sum types and exhaustivity checking together completely prevent this. So sum types enforce that all cases are handled properly. Exhaustivity checking enforces that you've handled all the cases that are possible in your control flow. And a sum type would fix this by essentially returning either OK or an error. If it's OK, you get the value just fine. If it's an error, then you know for a fact that the EC recover did not work. You don't have to check a magic constant. There's a 0% chance that you are going to accidentally treat the error value as an address and then proceed. All right. Okay, so just a quick speed round of language features. Time is coming to an end here. Ifs are expressions. We have unchecked arithmetic as well as checked arithmetic without runtime overhead. That's due to our VM architecture. We have pretty sweet underscore syntax, just another little thing. Matches our expressions. Okay, I'll skip over visibility for time's sake. Both Solidity and Sway support writing inline assembly, but Sway's standard library is implemented in this construct. The way in which we do this is a little bit lower level for now. So in Solidity, an assembly block looks something like this. And if you're an optimizer, you'll end up doing this a lot. And in Sway, assembly blocks look a little bit more like this. You initialize some registers to some values. So in this case, the register R1 is initialized to A, R2 is initialized to B. We add those two. So if you're familiar with like a MIPS or x86 style assembly, R3 is the destination. So we're adding R1 and R2, putting it in R3, and then returning R3 with an implicit return. A couple more assembly examples here. You can put any arbitrary expression in the initializer of your assembly. Let's see. Okay, cool. So the final point that I want to hit here in the last 5 minutes is our tooling, and I think this is honestly the biggest selling point. So the language itself, sure, it's like learned a lot from modern language development and modern language design, and it tries to make everything safe, and it tries to make everything ergonomic. But in addition to that, we package it with good tooling. And one of our main points of pride is this thing called Fork. So our organization is called Fuel, and this stands for Fuel Orchestrator. And this is going to be your cargo. This is going to let you build. This is going to let you test. This is going to let you eventually audit your code. This lets you initialize new projects, et cetera, et cetera. And all of this is completely enshrined. It's all open source as well, but it's like the enshrined and recommended way of doing things. And we also subscribe to the Rust philosophy of one way to do everything, and that one way should be the correct way, and it should be also the most efficient way. We also have 2 SDKs available for dealing with our contract code. So the Rust SDK, what it does is it allows you to test, deploy to a node, do all sorts of things. Both of these SDKs allow you to do that, and you can do them either from Rust or from TypeScript. So this is going to also not quite fit on the screen up here, but this is just an example of the Rust code that you would, see if I can do this. The Rust code that would be used to, for example, load a contract. Can I do it from here? Load a contract and interact with it from Rust using our SDK. We don't need to delve into this in too much detail, but you can get a general idea for the fact that we have an ergonomic API that surrounds contracts in Rust so that you're able to programmatically deploy and test repeatably. And with just 3 minutes to spare, I will wrap it up. Thank you all for listening. Check out Sway if you're interested in using it. We have an email there, devprogram@fuel.sh. We also have a Discord server. We have multiple Twitters. Sway Lang has a Twitter as well. And yeah, that's all.
Thanks a lot. I wanted to ask, actually, what's your target audience for this language? So what types of products should be built with it?
Yeah, so that's a good question. So just to give you some context, I'm the compiler guy. I work on primarily the language, but we also have a layer 2 rollup, and we also have a modular blockchain execution layer. And so if you're interested in layer 2s and scaling in general, this is like a perfect chance to dive in. I know there's a lot of competing contract development platforms in the layer 2 space, but this is one of them. So that's one use case. Another thing is if performance is really key, so you have maybe high volume trading and you're worried about gas fees or things like that, that's a really good use case. But it is a general purpose contract development platform, so ideally any contract where you care about security and performance could be applied here.
Okay, but it's compiled, it's EVM compatible, yeah?
Actually, it's not. So we do have an EVM compatible VM, and that's part of the optimistic rollup project. However, this language targets specifically the FuelVM opcodes. So that's, in that way, it would be EVM compatible. Although we've recently pivoted to essentially working more with Celestia, if you're familiar with a company called Celestia, and providing the first modular blockchain execution environment, and we aim to be the fastest in that space.
Great, thank you very much. Any more questions?
Okay, how would you compare the language with Viper?
Yes. So Viper, for those not familiar, is like a Python-based smart contract development platform as well. Viper's really cool, and yeah, I mean, it's definitely a really cool product. We're kind of taking a different design philosophy, though, obviously, for 2 main reasons. One is we're targeting the FuelVM and our specific layer 2, and that involves entirely different opcodes, and so we're not really able to leverage things like Viper for our toolchain, and that's just kind of necessarily why that justifies the existence of this project. But additionally, in language philosophy, like I mentioned, I'm like the language guy, and in language philosophy, very different. Python has a lot of pros about it, but we're definitely more interested in static analysis, security, auditability, things like that at compile time. So we want the compiler to be able to tell you, hey, this could be a vulnerability that could be in your contract. And that's not as high of a priority as far as I'm aware in like the Viper toolkit. All right.
Any more questions? Oh, yeah.
Something easy.
Thank you very much. In fact, I've got 3 questions very quickly. One about Remix. Is there any plan to support the language via Remix itself as an IDE? And question number 2, is there any porting tool? Like I already have my own Solidity smart contract and I would like to port it or convert it to be using Sway language. And question number 3, in the market there is a very famous library, OpenZeppelin. Is there any way to utilize it, or is there any chance that this library is going to be ported to Sway?
Okay, yeah. So just to give some context, we're still a pretty relatively early stages project. We're about a year in. And I'm going to kind of answer these, well, I'll start back to front since I remember them. So question 3, OpenZeppelin. It would be great to have tooling like that available. We're still a pretty early project, and we ourselves haven't invested the resources in implementing it inside of our organization. It would be great if once it's out there and we're seeing more adoption, it's entirely possible that somebody would implement that, or even that we would pay to have that implemented. But that's not right now. We're still working on core language development and the tool chain itself. Question 2 was a transpiler, so like going from Solidity to Sway. That is also something that would be obviously really good for us to have for adoption's sake, but that's a really hairy problem, especially when the destination language is still being developed. So that's one of those maybe someday things. It would be really great, but I know I believe there's one for Cairo, right? That you can go from Solidity to Cairo, I think, if I'm not mistaken. And that's like a really cool thing, but yeah, we don't have that yet. And the first one you said limits, is that what you said? Linux IDE? Oh, Emacs. Did you say Emacs? Oh, okay. Yeah, so as part of tooling, we have a Vim plugin and a VS Code plugin. Unfortunately, not Emacs, but we have a core language server. So for Emacs, if you have, I'm personally a Vim person, so I'm sure there's a language server protocol that's Emacs compatible that you could use, but we do have a language server. Yeah. Anything else?
Is that it? Or any more questions? Okay, it seems that we're done. Thank you. You're really doing cool stuff. Please check it out.